Okay, let's get started here for this next talk. Rob Martinson, CTO at nLIGHT, and on this particular talk, it's been a very special project over the past year, working with Marco and his team at Aconity, and Marcin's team in Santa Fe, New Mexico at Flow3D. And it's a collaboration where we combined the numerical modeling capability of Flow3D with the empirical work that Marco did all the heavy lifting on. But so Marco just got his master's degree at Aachen University, and he currently works for Aconity 3D. And Marcin is Dr. Marcin Serdeczny. Sorry, hopefully I didn't butcher that too much. Is responsible for training people on the use of these numerical simulation tools by Flow3D for Central Europe. Okay, he's based in Copenhagen, and let's start the talk with Marco. Thank you.
Thanks, Rob, for introducing. So thanks for coming and welcome to the nLIGHT booth and to our presentation. Today we are going to talk about 4D printing, and we start with a little motivation. So what actually is 4D printing before we present the current state with processing, mechanical properties, some results, and metallography, as well as the simulation part by Marcin. And in the end, we will give a conclusion. So starting with the question, what actually is 4D printing? As you may know, LPBF generally is a process where a heat source, namely a laser, interacts with a metal powder and melts it. And by doing so, we go in the X and Y direction, giving us the first two dimensions. Adding layer by layer gives us the third dimension. But what could the fourth dimension be? As you may also know, LPBF generally is a very complex process where many influencing factors and interactions of various effects take place, which are not fully understood yet. They lead to the thermal field and thus the solidification conditions, and in the end they determine the material parts properties and the part quality. And since they determine the part quality and the part properties, it's absolutely crucial to gain knowledge about these parameters and to get control over the parameters within the process to tailor your physical properties. One main influencing factor here is the intensity distribution of the laser. And while common lasers operating with a standard Gaussian beam need to be complemented with complex setups, the nLIGHT AFX is able to set 7 different intensity distributions within the process in 30 milliseconds. And doing so, we have index 0 as the standard Gaussian beam, index 6 as a ring profile, and 5 indices in between. So we are going to have intensity distribution as an additional process parameter, and this is our fourth dimension in handling this easy different intensity distributions. To investigate this innovative laser, we set up different experiments, broad parameter study with a nickel-based super alloy in 718, varying laser powder, power, scan speed, hedge distance, and layer thickness. We chose 3 out of 7 different intensity distributions, the index 0 as the representative for the Gaussian beam, index 6 the ring profile, and index 3 as a combination of both. Additionally, we defocused the spot of index 0 just to be sure that there is no other influence of differing spot sizes. Otherwise, constant process conditions enabled us to investigate the isolated influence of the different intensity distributions on the final parts. And out of this, we generated processing windows just to get a first impression of the productivity and processability. These were the base grounds for the decision to select further parameters to produce and test tensile specimen, as well as the metallographic analysis via LOM, SEM, EBSD, and EDX. Coming up to the results, here we see the processing windows for index 0 and index 6. As you may see, first of all, the black X's are parts which were not processable, The blue ones were processable, and those with a green circle are with a density higher than 99.5. And as you may see here, the processing window for index 6 is a little broader, especially in the region of higher energy density. And first further experiments revealed that, even at higher power and higher scan speed, there were parts processable, leading to the assumption that increased process stability may be with the index 6. The results of the mechanical properties are indeed much greater. So what we can see here is a really interesting thing. On the left side we have the yield strength, on the right side the elongation, and as you may see, by using index 6 we can increase the yield strength and tensor strength as well as the elongation at break. And in comparison to index 0, almost as double as high in the elongation at break. Searching for the reason, we took a look at the metallography, especially at the edge cross sections, but there were no big difference between the indices, as well as the further analysis via SEM in terms of primary dendrite arm spacing and EDX, the segregation behavior. But looking at the EBSD images, showed the reason, so to say. On the left side we have the sample of index 0 with different grain orientations, while on the right side we have the sample of index 6 with straight columnar elongated grains parallel to the build direction. And this texture may help us to explain the differing mechanical properties. Having more elongated grains parallel to the build, and in our case also the load direction, meaning less perpendicular grain boundaries to the load direction. And since grain boundaries are invincible obstacles for dislocation, dislocation movement is favored in the case of index 6, leading to a higher plastic deformation and thus a higher elongation at break. So we can explain the differing mechanical properties by the texture. And now it's the question, why is this texture so differing? One approach was that the microstructure was the reason, but as we have seen before, there were no big difference in the microstructure in terms of PDAA and segregation behavior, which are a direct consequence of the thermal history. And thus the assumption came up that there might be not that much different thermal field by using the different intensity distributions. One explanatory approach could be the melt-pool shape. As we may see here on the left side, the melt-pool shape of index 0 is much narrower and deeper in comparison to the sample of index 6, which is much wider and flatter. And generally, the dendrite growth occurs perpendicular to the melt-pool boundary. In case of a flatter melt-pool, we have more dendrites aligned parallel to each other and to the build and load direction, while on the left side we have dendrites growing to the center of the melt-pool, meaning a higher competitive growth of dendrites and leading thus to different grain orientations. While on the right side we have dendrites growing over many layers and thus grains over many layers, coming up to this sharp texture and the differences in the texture. So we can explain the different textures by the melt-pool shapes, and the different textures are the reason for the different mechanical properties. And to get a deeper insight in these physics behind the interaction of laser and material, experts from flow science have made a big effort. So welcome, Marcin, again, and the stage is yours.
Thank you very much, Marco. My name is Marcin. Once again, I'll be presenting the work of my colleague from Flow Science as well, Ibai Mujica. So we, as a company that actually produces CFD software, we got interested in this problem and the project, and we wanted to contribute with and to check also whether our model can show the physical explanations, and also to take a first step on giving a tool for better control of this phenomenon that we've been observing. But before we dive into it, I would like to just say a few words about what actually CFD is, which is the software that we're developing. So CFD, or Computational Fluid Dynamics, relies on solving the solving the fundamental conservation equations of fluid motions, and these are usually the conservation of mass, momentum, and energy. And That information on its own, which is the pressure field, velocity field, and the temperature field, is already a very useful result for many engineers. But the beauty of it also lies in the fact that we can add on many empirical and analytical models that can give us a further insight. So to sum up, the strength of CFD lies in the fact that we can apply it very often to the engineering real examples, like in this case, the laser powder bed fusion. On the contrary to, for example, analytical models, it can deliver explanations of the physical phenomena thanks to this insight into the many variables in the flow field. And also, by having this insight, we can design the products and processes better. And once we have the model that is working, it is often much more cost effective to do actually the analysis for CFD than the actual experiments. But it's not only that there are advantages, there are of course some challenges. It's usually a time-consuming process. It takes time to develop a good model and then do the simulations. It is a complex process, in essence, that it takes a required engineer and some knowledge to do it. And it bears some uncertainty, as the accuracy of the CFD simulation basis on the input parameters that we're providing for the model, and the fact that this is a model itself, which is some kind of approximation of the real world. And this is what we've been doing in flow science for 40 years. We are a developer of CFD software, and we have an experience in many different applications ranging from water and environment, and also casting applications. But we're also strengthening our portfolio in the AM processes, in material extrusion, binder jetting, but also laser powder bed fusion and directed energy deposition. So here is actually an example of the simulation with the heat distribution as in index 6, where the laser scans through the powder and it melts the powder, giving the insight of the Multipool dynamics. So now a little bit about the model for this particular project. So in any numerical simulation, we first define the geometry and the mesh. In this case, we have arrived with this quite simple rectangular geometry with an average cell size of 5 microns, which is basically the discretization with which we're going to solve the governing equations. And that yielded a total cell count of around 3.6 million cells. In the software itself, we can, of course, implement the different heat flux distributions in the radial direction. So in this case, for this project, the 3 different indices were chosen. And of course, we kept the other laser parameters the same as in the experiment, which is total power of 700 watts and the scanning speed of 1.25 meters per second and the laser spot diameter of 190 microns. Next step in setting up the simulation is to decide which of the physical models we would like to include, and that's also the beauty of the CFD, that we can sometimes switch off part of the physics to see which of them is actually governing for the problem. So of course we do want to consider the heat transfer, which is basically telling the code to solve the energy equation. We evaluate the density as a function of the temperature to account for things like buoyancy-driven flows. The molten metal is approximated as a viscous fluid, and it flows in a laminar regime. The solidification model takes care of how the flow is resolved in the mashy region, where the fluid is between the solidus and the liquidus temperature. The surface tension is also an important effect here in this process. And of course, we have everything in a gravitational field. On top of that, we can add the laser-specific or laser process models, such as multiple reflection model, which is a model that accounts for the fact that if laser ray hits the material and it's part of the energy is absorbed, but part of it is reflected, and it can actually hit some other fluid or a powder particle and also absorb this energy. We also included in this model the recoil pressure model, which accounts for the fact that the evaporating liquid metal expands very rapidly, and it creates a force on the free surface of the molten material. And that actually is one of the important drivers of the flow inside of the Multipool. As in any simulation, we do include, of course, the material parameters of the material itself. In this case, it was Inconel 718. And we need to set some boundary conditions. In this case, it was a symmetry boundary, or an adiabatic boundary, if you will, on the 5 of the faces of the domain. And the 6th domain from the top was a pressure boundary, which was essentially approximating the inert gas atmosphere. So first of the results slides, here I would like to show you the comparison between the cross-sectional shapes of the multipool from the model and together with the experimental results. So what we can see here, what Marco has already mentioned, is that when we change this heat flux distribution by moving the amount of heat from the center to the outer ring of the laser beam, actually the multipool shape becomes wider and shallower. And this is what we do capture in the model, which is a very positive result because it shows us that there is a qualitative agreement of the influence of this parameter on the multipool shape. And it shows us that we're on the right track with using the model. Next, we look deeper into what happens actually in the multipool. And one of the useful information that we can get out of the simulation is the solidification temperature gradient. And what we can see here is that solidification temperature gradient vectors are all pointing towards the center of the multipool, which is the center of the laser beam. And actually, by the pure fact of making the multipool shape wider and shallower, more of them starts to be parallel to each other and actually pointing in the Z direction, which would be one of the indicator where comes the parallel dendrite growth in this process, which corresponds to the increased mechanical properties. Another useful information for many of those who are actually working with the laser powder bed fusion is, for example, the solidification cooling rate, at which we can look at to feed it further on to the microstructural models. We have also taken a look at the velocity flow field in this problem. And what we can see here is that the velocity field for index 0 and index 3 shows that most of the velocity vectors is actually directed to the back of the laser beams, or sort of to the behind of the multipool. While for the index 6, we can see that some of the arrows are also oriented to the front of the multipool. And in general, the average velocity of the multipool inside the multipool is lower for the index 6, which also corresponds to a more stable behavior of the multipool and less of the spatter of the material. And here on the bottom, what I have shown here is the evaporation pressure, which is what I mentioned at the beginning, is the pressure coming out from the expanding or rapidly evaporating gas at the molten interface. And is what we think one of the main driver for this change in the velocities, because as you can see, the maxima of these evaporation pressure are actually shifting a little bit to the outer ring when we change the heat flux distribution. So this will be our contribution. I'll just give the stage back to Marco to sum up our study.
Yeah, thanks for the great presentation. And what we saw is that we will get to know something behind the physics of the interaction of laser and material, which can help us to explain what is going on in the process. And what we also saw is that it is possible to adjust targeted textures and mechanical properties, and that 4D printing can give a huge potential for high temperature application, for example, the creep resistance, and not only within built jobs, but also within parts and also layers. We are not at the end. Next steps would be the further analysis of anisotropy, different analysis via SEM, EBSD of different parameter sets, references with index 0 focused, so what's the influence of defocusing, and of course different heat treatments to investigate the influence for heat treatments for different parameter sets. As a conclusion, we can say that 4D printing may lead to complete new thinking of sample applications, and this may be beyond our imagination at the current point in time, but we would like you now to think with us together about it. Thank you for your attention.
So any questions for the speakers? Now, all this work was with Inconel 718?
Nickel-based superalloy, yeah. So equivalent to Inconel, right? sorry for the mic. Yeah, right. Nickel-based superalloy. Yeah.
Well, let's thank our speakers one more time. Thank you.
Okay. Thanks.